Okay, again, log base 2 versus x. We just reverse the columns of the 2 to the x function, and we get these columns. So we understand that these are valid. Okay, we can extend this a little bit. Okay, if we want to go to 3, 4, 5 here, we would get 8, 16, 32. And the numbers go on. Okay, by the time we get out to 10 here, we need 1024 over here. So we don't have to go that much further to get into 4-digit numbers. And if we go to 20, we need to have 1,000,000 over here. That's fairly easy to see. And if we go in this direction, if we go to -3 and -4, we get 1/8, 1/16, and so forth on up the line. Okay, well, that's our base 2 logs. What about our log log? And log of x means log base 10 of x. So this is our base 10 log. Well, we can start kind of in the middle here. You know, we could have -2, -1, 0, 1, 2. And our base 10 logs would be, well, this would be the reverse of a 10 to the x table. So if we have 0 here, we have to have 10 to the 0 here. Well, that's 1. If we have 1 here, we have to have 10 to the 1 here, which is 10. If we have 2 here, we have to have 10 to the second, which is 100. If we have -1 here, this is going to be 10 to the -1, which is 0.1. 10 to the -2 is 0.01. Well, we definitely see a pattern here. Okay? In the sequence 1, 10, 100, each number is 10 times as much as the previous. So we're going to have 1,000, 10,000, 100,000, and if we want to go this far, 1,000,000. And that's if we go to 3, 4, 5, and 6. Now, a quick and dirty way to remember this, although you want to remember where this comes from, is simply that the number of zeros you have here is equal to this number. Okay? So if you want to write, now I did an estimate yesterday in the newspaper. They asked, what's the approximate weight of the atmosphere? Well, I know the values of the constants and so forth, so I calculated in my head. The one calculation I didn't understand, I wasn't sure of, was how high you have to go in the atmosphere to get half the weight of the atmosphere. I was estimating 3,000 meters. Okay? I believe that estimate was a little low because I came out a little low. I came out with like 3 times 10 to the 15th tons, when the answer was 5 times 10 to the 15th tons. So obviously I had a light atmosphere in my mind when I did that. Well, whether that was it or not, it's just, uncertainty in how far you got to go before you get half the atmosphere. If you go up to 4,000 meters, that comes out pretty close. And I was using the fact that the density of the atmosphere decreases exponentially. It's an exponential function decrease. So I immediately pulled out stuff that we happen to be doing here. It's just, they have these questions. Occasionally they're good questions. What's the weight of rainfall that falls on the earth in a year? I came out fairly close on that one. But that didn't involve exponential. That just involves areas and volumes and stuff. That was simple. So my point is, though, if you wanted to estimate the weight of the atmosphere for some reason, you'd be up to 10 to the 15th tons. Okay? And if you want to do it in pounds, you'd be up to the 10 to the 18th. It would make sense to get a handle on those numbers to talk about their logarithms. Okay? And 10 to the 18th, the logarithm is just 18, right? So, when you're talking about the intensity of sound, if I talk in a low voice versus a pretty high voice, that second sound was probably at least 10,000 times, maybe 100,000 times as intense as the other one. Okay? To talk about that, you really want to use a logarithmic scale. So it's like 5 points in a logarithmic scale or 4 points. And you multiply that by 10 and you get the decibel difference. Okay, so log scales are important, and it's important to have a feeling for what the numbers that correspond to the logarithms actually mean. Well, with that digression, let's go in this direction from 1. What we're doing is we have a 0.1 and a 0.01. We're basically adding a 0, and it's easy to see why. Every time we go 1 unit in this direction, everything becomes 1/10 as great, and as soon as we start adding zeros after the decimal point, you're just going to add an extra 0 every time. Okay, so there's our log base 10 table. You don't want to try to graph this. If you have a graph where 1 is this far, where's a million? Okay? Well, a million is miles and miles away. Okay? If a tenth is this big, then 10,000 is going to be about a mile high. A million is going to be 100 times that. It's going to be 100 miles high. Pretty much out of the atmosphere, where the exponential decrease in density means you don't have much of it. Okay? So anyhow, there's an intuitive connection with logarithms, and you kind of need that to do some of these problems. You can make estimates of logarithms. Okay, so, well, let's estimate log base 10 of 7,000. Okay. Well, it's hard to make a very accurate estimate of this because the concavity of the graph is fairly extreme, and it's hard to take the concavity into account unless you're experienced with doing that. Now I can kind of do it, but even at that, if I don't have a picture, I got to picture it in my mind, and I can easily be off by a little bit at least. But we can say that log base 10 of 7,000, well, here's a table. And you don't even really need a table. You know it's between the log base 10 of 1,000 and the log base 10 of 10,000. And it's going to go somewhere between here and here on the table. And if you've got a table, you can say, well, that's going to put it between 3 and 4. And 7,000 is closer to 10,000 than it is to 1,000. So you figure it's going to be pretty close, or at least closer to 4. Okay? It's probably going to be closer to 4. So my estimate is about I'm going to say 3.8. I think it's at least that. And that's because of the concavity of the thing, and I happen to know that log of 3,000 would be about 3.5, and he's still got quite a ways to go to get to 7,000. So it's between 3.8 and 3.9. I'm pretty sure of that. Now, if I refresh my memory on certain logs, I could make a better estimate. But estimating's not really the point. If you're making an estimate, then even if you estimated 3.7, it would still be a reasonable estimate. Okay? Yes, I refine a reasonable estimate and say it's about 3.8. And probably a little more than that. But understand how that's a pretty reasonable estimate of this log. Although if you did it, you might want to think 3.7. It's going to be a little higher than you think it's going to be. Okay? Now that's just there to give you a ballpark picture. Okay? If I say that this sound is 7,000 times the intensity of another sound, well, the log of that is 3.8. You multiply it by 10 for a reason I'm not going to talk about yet. You get 38, and you say, okay, that's going to be about 38 decibels higher. Okay? 38 decibels means one sound is about 7,000 times the other. Now, you don't have to know that. We haven't talked about the decibel scale, but we will. Okay? Again, just the idea of understanding that this is log table. Once you get used to base 10 logs, you don't really need a table to figure out that 7,000 is between 1,000 and 4,000. And the log of 1,000 is 3, log of 4,000 is 4, etc. Okay, well, that's about all I really have to say at this point. Give me a second to do what I really want to do with the recording, which is pause it. Pause recording.
Recording stopped.
Okay, and let me turn this thing off.